So we have done something very important here. Okay, now, first point, try to understand the take-home message. 6 commutation relations, simultaneous eigenstate of J squared and a component called JZ. There are restrictions summarized in this box. Okay. Then if you are really interested, try to go into the detail, follow all the steps, try to go through the arguments by yourself in private at a quiet place. There's something that cannot be taught explicitly in physics. You have to work it out step by step, talk to yourself, explain to yourself until you are comfortable with every argument. And then after that, you really know the proof. Okay? Nonetheless, the proof is not as important as the result, I must say. So let me continue. The remaining pages are just remarks to make connections to what you learn and to what we will be doing. Okay? Now, first of all, this box is the most general statement about angular momentum in quantum mechanics, defined by the commutation relations only. And then it provides 2 possibilities. The J quantum number can take on either half integers or integers. You have seen this in different contexts before. For the integer choice, you have seen it in orbital angular momentum in atoms. This is the YLM theta phi. L must be positive integers. For the half integer, you have seen one case, electron spin, which is J equals half, but it's so important that in that context, you have a new symbol called S. Then you may wonder, in the orbital angular momentum situation, why is the half integer rejected? That possibility is not realized. Now you go back to what you did in orbital angular momentum. You solve it in the theta phi spherical coordinates. That is to say, you solve it in a particular real space of the particle with the angular coordinates theta phi. In this context, more physics is fit into the problem. The particular one is the single valued requirement. When the phi angle, you start with somewhere, turn 2 pi back to the same place, the single valuedness of the wave function require that the phi function, after you add 2 pi to the angle phi, must go back to the same value. If you remember, the LZ operator is something like d phi. I think it's IH bar d phi, right? Okay. So you have this GIM phi in the phi part of the spherical harmonics. With this additional requirement, this m value can only take on integer. Therefore, this particular additional requirement, single value that's here, okay, ban the other possibility of half integer. There's no contradiction, you must realize. The commutation relations provide both possibilities. When you solve for the orbital thing, you are including additional requirement more than the commutation relations only. That fouls out half integer option. Okay, nothing in contradiction with what we just got. We also have sin spin. Spin takes on this j equals half possibility. Okay, so nature is very clever. It makes use of both options. You have seen it in orbital integer, you have seen it in spin, the half. Okay, but you haven't seen anything else because it's not possible. So finally, some notation. In a rather abstract or direct way, we can label the eigenstate, simultaneous eigenstate of j squared, which carry the quantum number j, and the z component, which carries the mj component in this abstract form. And our restrictions or conditions become the following. The j square operator for this simultaneous eigenstate, the magnitude square has this particular form of eigenvalue, with j taking on either half integer or integers. Well, must be positive, okay? And then the z component in this abstract notation, the second label, quantum number mj, give you the z quantum, z component eigenvalues. And mj can take on values from plus j to minus j instead of 1. All right, so 21 is the abstract form of 20. Okay, this is inverse. This is in the mathematical form. They mean the same thing, nothing fancy. All right. And now, this is slightly beyond our level, okay? But we are very close, maybe 1 or 2 steps, and then we can go there. I just want to write down several, actually one formula. So we have worked out that if we operate j plus on this state, it will increase this by 1. If we operate j minus on this simultaneous eigenstate, it will decrease the z component by 1, the quantum number, okay, by h bar in values, okay? So therefore, it would be interesting to look for what is this proportionality constant. There's a constant in front, all right? Now, that is a harder, well, more tedious thing, but we are very close to it. Remember that we have seen this relationships. Then it is easy to find out that there are some funny factors like this one. Okay, j plus 1 minus mj with j minus j plus 1, things like that. Okay, now you can use this to work out all these coefficients. This falls into a chapter in advanced quantum mechanics called finding the Kapch-Gordon coefficients. But for our course, we don't need such technical details. But here I just would like to mention that we are very close to that, but we don't want to burden you with so much technical stuff. The big picture is the most important. All right. So now we can step into something that basically is to apply what we just learned. Okay. Sorry. Do you see a new section called total angular momentum? Is that right? Okay, good. So now we can start playing with more angular momentum in quantum mechanics. Previously, we only know orbital from solving the hydrogen atom central force problems. And then we have this Stern-Gerlach experiment telling us there's something called spin. We are only restricted to these two quantities. However, as motivated in today's lecture, we need to consider adding up the orbital angular momentum of the electron in the hydrogen and its own spin angular momentum. So therefore, we are motivated to study something called total angular momentum. So this is the simplest situation, actually, because let's think about the hydrogen atom. There's only one electron, so there is only one orbital angular momentum L, depending on which state the electron is in. There's only a spin half because one electron, all right? So we want to see how can we add this into a total angular momentum called J. Since this is an angular momentum, this is an angular momentum, this is also an angular momentum, all right? Therefore, what we learned in the past hour worked for J. So without doing anything, we know that J squared must be of the form this one, okay? And the Z component, JZ, must have eigenvalue like this. The question is, what are the possible values of J? All right. For example, if this is a P state, L equals 1. This is spin half, S is always half. We add this into a new total angular momentum. What are the possible values of J? That is the question. Okay. So let me, at the same time, do a little bit of atomic physics within this context. So in full, how can we describe the electron in a hydrogen atom, its spatial wave function and its spin wave function? This is the 2x1 column, if you like, in the matrix representation of Pauli. So in the past, in last term, you learned this thing in separate chapters. So you have this so-called alpha theta phi spatial part. You need 3 quantum numbers, N, L, ML, in which these two actually are describing the orbital angular momentum. Then, in the last chapter of last term, you did a lot of spins, and you know electron spin is always half the quantum number S, and the Z component can be plus half, minus half. All right. So in full, actually, we need 5 quantum numbers to be complete. The first 3 has to do with spatial part. The last 2 is about spin. But for single electron, this magnitude square of the spin of an electron is a boring half quantum number. It means the following. The S magnitude is always a constant. All right. Since it is a constant, always half, very often we will omit or skip this and use 4 numbers to label the electron in a hydrogen. The 3 spatial one and the last one plus minus half for the Z component of the spin, or up, down, if you like. And it is in this situation that we only need 4, but actually behind the scene, there is a magnitude square of the spin that is a constant, that we are lazy. We don't want to say it again and again. So you don't see that half written down here. It should be there, okay, to be absolutely clear. For example, in helium, you have 2 electrons. Just like last time, before the New Year break, there are questions about how to, when you have 2 electrons, then we will have up, up, down, down, up, down, down, up, things like that. Then you need to label, you need a 5th label here about what is the total spin when you add up 2 spin half. But for 1 electron, we can be lazy. That's perfectly all right. But I intentionally make a space here to remind you there should be something there, but we are just too lazy to write it down, all right? Then we have 4 numbers, and usually that can be written as ground state 100 plus, or 100 up, or 100 alpha, or 100 chi Z, things like that, okay? The other one is similar, okay? So you have the minus half, or down, or using a 0, 1 column, etc. Now, we can also invoke something different in the description. What I mean is the following. We have the orbital part, we have the spin part. What if we add these 2 things up to form a total, and then how could we describe this combined orbital and spin part? We are going to exchange these 4 numbers into 4 numbers. So let me advertise what we are going to do. We will change this 4 into L, so the same thing, S, the same thing, the boring half, and then we will change it to J, the total angular momentum, magnitude, and the Z component. Instead of using orbital and spin separately, we want to add them up and then describe the total angular momentum of this combination. You may wonder why. That will come later. Simple answer is, since L and S will couple, will interact, we will need J. If we don't have interaction, then why are we doing that? Mathematically, in one sentence, they are just linear combinations of each other. We can do that. Whether it is a good thing to do, a bad thing to do, it depends on the situation. But mathematically, you have this states, I have another set of states, one can be expressed in terms of the other. So let's develop it further. So we can define a total, I call it J equals L plus S. But now we realize that angular momentum, 6 commutation relation satisfied by L, and other 6 commutation relations satisfied by S, you add them up. For example, Jx is just Lx plus Sx. Lx will act upon things in theta phi space. Sx will look for some column thing to operate. They operate on different things. Therefore, Lx, Sx, they commute between themselves, or everything about L and everything about S, they commute between themselves. All right. So it is easy to prove that Jx, Jy, Jz also obey the same commutation relations. All right. And then J square is defined as L plus S square. Okay. Again, you can show that J square commute with Jx, Jy, Jz. Thereby, J satisfy the same 6 commutation relation that we called them a angular momentum, to define angular momentum in quantum mechanics. Nice. Immediately, we can copy results through. We know that whatever this is, thing turns out to be, J square must take on eigenvalues of this form. And this number can only be integer or half integer, must be positive. Once a J is decided, Mj can only take on 2J plus 1 values. All right, now that is the nice thing that for the hard work that we did. We worked through it, we work out the general thing, and now we are very comfortable to claim now, whatever it is, it must be the same form. The question becomes, what are the allowed values of this J if we know the allowed value of this L and S? Okay, so this is the question. For example, you have a P state. L is 1. 1 electron, S is half. Then what are the values of J? Okay, now I will state the result. I will not prove the results for you because this is beyond this course. In the next more advanced course, there's a whole chapter about addition of angular momentum. You will get what I just mentioned about Kapsch-Gordon coefficient or the how to linear combine things, okay? But for our purpose of understanding atoms, molecules, and nuclei, we only need some rules, and here's the rule. So now, for 1 electron, S is always half. For a given state, L, the possible J values are, if L is not 0, then it could be L plus half and L minus half. So it is like this number minus S, this number plus S, okay? But if it is an S state, L equals 0, remember, J cannot be negative. If we allow L minus half, it becomes minus half is wrong from the general result. Therefore, when it is an S state, only L plus S, 0 plus half is allowed. So J is half. Okay, so 22 here is something that you should know, and you should know how to apply. I'm not claiming that I have explained it or derived that. I'm not going to do that. Here, it is more troublesome than taking it in understand the meaning, and apply it. All right. Now I would further explore what it means, just to get to the point that you will think that it makes sense. First, look at some examples. First of all, first point to notice is that the accounting is correct. 會計啊, okay, what does it mean? The number of states will be no more, no less in the two different descriptions. Let me explain what it means. Let's go back to what you learned in the past, in the last course. I have an hydrogen, 2p state, okay? L is 1. We know that orbital angular momentum, L is 1 means ML is 1, 0, minus 1. All right? Or PX, PY, PZ if you like, okay? But PX is a combination of these two things, all right? So you have spin half, therefore MS is plus minus half. Together you have 6 p states, because this can be plus minus half, this can be plus minus half, this can be plus minus half. Okay? So let me summarize. If I use the ordinary L and S description, I have 6 states. All right? So this is this description. L is 1, L is half. Now I can play with these two indices, these two numbers, and there are 6 combinations. 1 up, 1 down, 0 up, 0 down, minus 1 up, minus 1 down. Follow me? Okay? 6 is the number. Now, I'm going to apply this rule. I want to define a total angular momentum, which is L plus S. And I just listed the rule to define the J square point eigenvalues. J will be L plus S, L plus half, so 3/2, or L minus half, half. 2 possible values. Let's count. For general angular momentum, for J, the maximum component is 3/2. The Z component can take on from the maximum to the negative maximum in step of 1. So there are 4 values. For J is half, there are 2 values. You see, altogether there are 6. No more, no less. Therefore, if we switch the description to L is 1, S is half, I need these 2 numbers because I list here so that I know the possible numbers of J. And now if I use JMJ to describe the situation, I have 3/2 under which there are 4 numbers. Then I have J is half under which MJ there are 2 numbers. There are also 6 steps. No more, no less. Accounting is correct. Okay? So at this level, at least, there are no contradiction. You have this P state to describe. I can label it this way, the first way, or I can label them the other way. No more, no less, different labeling. Then the question naturally is, which labeling is better? the wrong answer will be one of them is better. It is not scientific. The scientific and logical answer is it depends on the situation. You tell me more. Are they going to be coupled? If they are not coupled, they are both as good. Do the same thing. But if S and L are going to be coupled in the Hamiltonian, then you have no choice but to invoke the total angular momentum. So a logical answer is, which one is better? It depends on the situation, depends on the physical context, depends on the problems you have in hand, all right? Be logical when you study science, in particular physics. So this page only summarized what I explained on the last page. One exercise for you, play with D state. So I have L equals 2, I have spin up, down, there are 10 states, right? You know, the transition elements in the periodic table, 3D. Iron, nickel, copper, iron, nickel, cobalt, all there, very important magnetic materials, all right? Now try to label it using JMJ and make sure that you account for the same number, 10 states, no more, no less. So the big picture, here I give you the big picture, but you don't need to know the mathematical detail. The big picture is as follows. For the P states, I have 6 states. The old labeling will be P state L equals 1, spin half, and then I have this 6 states. Now I switch label to JMJ, total angular momentum. Obviously, there are 6 states into a black box and 6 states coming out in this label. Mathematically, it means each one of them is a linear combination of these 6 states. So each one will have 6 coefficients to look for, all right? And this is what I already mentioned. They are called the Kapch-Gordon coefficients. It is a rather complicated thing to obtain. You need a lot of operator algebra. Nonetheless, there are tables to look up. That's the nice thing, okay? So you only need to know the big picture. If you don't want to work them out, look up tables. They're Kapch-Gordon coefficients tables to add up, say, L is 2, add to a spin half, what are the combinations? But the big picture is important. No more, no less. This is what you learned last course. If you want to add up L and S, you have total angular momentum description. But just like quantum mechanics, these are linear combinations of the 6 states. By that, you mean there are many coefficients in front to look for. Then, as I said, which one is better depends on the situation. If we only have the hydrogen atom, Hamiltonian only, which I mean is minus h bar squared over 2m minus the Coulomb. Okay, so this is your H atom, then both sets are equally good. However, when we have spin-orbit interaction, we are playing with the simple Hamiltonian plus something. And this particular something is of this form. You have a S dot L term. This is how spin and orbital angular momentum become coupled, interact. They dot into each other, all right? Now, immediately you see something very troublesome. A dot product means the following, right? Understand? Okay. So you immediately see something. Since this X, Y, Z of S, they themselves do not commute. L, X, Y, Z, they themselves do not commute. All right. Now, if you stayed on the Z description of orbital angular momentum, ML, and the Z description of spin, MS, that will be troublesome. Okay? Because with this term exists here, LZ is no longer commuting with the first term and the second term. All right? So we have to switch description to JMJ that will automatically take good care of this interaction term. So mathematically, it comes back to perturbation theory discussion that this will make the big matrix look easier when we change from that 6-state description to the new JMJ 6-state description. That will make that part of the matrix diagonal. Nice. Looks very nice. All right. So I think I need to stop here because of time. There are many interesting things here. So I will continue on this discussion to make the rule of adding L to a spin half reasonable to you. Okay. It's quite hard to derive formally all these rules, but and need not do so, but you get a good sense of why it works. Okay, so I will try to make that plausible to you on Thursday. Then after that, we will discuss the physics behind spin-orbit interaction, how this come about, and what is this constant in front. That is a very complicated constant. It turns out that physicists nowadays, especially those doing condensed matter physics, play with the prefactor that constant and then get some very interesting feature, topological insulator, etc., without buying a big magnet. Okay, because spin-orbit interaction is like a free of charge internal magnetic field. So I will continue the discussion on Thursday. So long for now. I will stay here to answer any questions.